Good morning friends. Today we are going to discuss about the numerical of exercise. Now up to the 9.17 we discuss. 9.18 at present we skip it. Right? We discuss later only on the base of the theory and that is not important. Now 9.19. What is this numerical? The one bulb is fixed on a wall of a room. The image of this bulb is obtained on opposite wall 3 meters away by a convex lens. Now, find the focal length, maximum possible focal length of a convex lens. Again, what it says that the one bulb is fixed on a one wall. The image of this bulb is obtained on the opposite wall. Opposite wall is at 3 meters distance from the first wall. That means there is the 3 meters away from the electric bulb. So its image is formed at the other wall, opposite wall. What is the maximum possible focal length of a convex lens? So in short, the distance between the object and image is given, that is the 3 meters. That is the 3 meters. Now listen. The maximum distance between object and image is same as, what is the u? Object distance, the same image distance is equal to 4f. Why the distance between these two is 4 times the focal length? We discuss later. Actually, there is the equation of derivation. Now, u is equal to v is equal to 4f. But here, the separation between the image and object is given the 3 meters. But u is equal to v is equal to 3 meters. Right? Therefore, 3 is equal to 4f. Therefore, focal length f is equal to 3 by 4. That means the 0.75 meter. Thus, focal length of a convex lens is 0.75 meter. So there is the answer. But why directly we are using this equation? The object distance, image distance is equal to 4 times of f. Already we discussed in case of a lens and mirror. As we place the object at C point, that means the center of curvature of a lens or the mirror. So its image is also formed at the same point on the other side. Right? Okay. In case of the mirror or the lens, there is the optical center C. As we place the object, its image is formed on the other side. That is the real inverted image. Okay. Now, there is the radius of curvature. We know that the relation between focal length and radius of curvature I is equal to 2f. Therefore, this distance is 2f. As the object is placed at the C point, so its image is also obtained at C point on the other side. So there is also the r distance. Therefore, there is also 2f distance. Now you can understand there is the object, there is the image. Distance between the object and image is 4f. Clear or not? So that is our object, that is our image. Clear this thing? So how we mathematically derive? For that purpose here, there is only for information, not for our requirement or the derivation. Only for information we derive this equation. Only for information. Which part is information? Suppose the object is, or the object distance is u. Therefore, from equation of length minus 1 upon u plus 1 upon v is equal to 1 upon f. Is equal to 1 upon f. Okay. Now, We acquired the relation u is equal to v is equal to 4f. So for that purpose, we consider one more diagram. That is the object O. That is the image I. That is the object distance u. That is the image distance v. Total distance is d. Total distance d. Right? Okay. But from figure, u plus v is equal to d. Therefore, v is equal to what? D minus u. D minus u. Here, object distance is negative, minus u. Therefore, this equation is 1 upon v is equal to. Now, equation 1 is 1 upon f is equal to 1 upon u plus 1 upon. Therefore, 1 upon v, 1 upon u plus, instead of the v, 1 upon d minus u. LCM is u into d minus u. Here, d minus u plus u cancel. 1 upon f. Therefore, u into d minus u is equal to fd. Therefore, ud minus u square is equal to fd. Therefore, u square minus ud plus df is equal to 0. Then the equation 2 is the quadratic equation of u. Is quadratic equation of. Now, what are the roots of this equation? The roots of equation 2 is u is equal to minus b plus or minus square root of b square minus 4c upon 2a. According to this equation, we can write here u is equal to minus d is minus d, therefore d, plus or minus b square, that means the b square, minus 4a 1 c f minus 4f upon 2a, a is 1, b square minus 4f. There is 4df, c is. But u is equal to v, therefore v is also d plus or minus square root of d square minus 4df upon 2. But now v is, image is real, image is real. Therefore, d square minus 4df must be greater than or is equal to 0. Therefore, d square greater than or is equal to 4df. dd cancel, therefore d is equal to 4. Thus, the distance between the object and image must be 4. Thus, distance between object and image is 4. So this part is only for your understanding, and also why the distance between the object and image is 4f. Directly we are using this equation in earlier numerical, and that is also helpful us in most of the objective question. Clear this? So this will be obtained, the d is equal to 4f, and already we know that as the object is placed on the center of curvature, so its image is also formed at the same point. Clear this? Okay. So that is very easy. Okay, now the next numerical is 9.20. Now the screen is placed at 90 centimeter distance from the object, and the image of the object formed by a convex lens for two different locations of a lens separated by 20 centimeter. Find the focal length of a convex lens. Now listen here, first thing, the distance between object and screen. D is given as the 90 centimeter. And distance between two location or the two position of a lens is given as the 20 centimeter. We have to find out focal length F of a lens. We have to find out. Here for convex lens is given. Convex lens is given. So what this numerical say there? There is the object. What is the object? And there is the screen. For two different positions of an object, we obtain the image on the same point, that means the screen. Suppose here the first position of the lens is this, L1. So object here, so its image is formed on the screen I. At that time, there is our object distance. Suppose this distance is x. This distance is x. So there is our u, remaining is our Clear this? Okay. Now, second location of this object is, suppose there is separated by 20 centimeter distance from the first position. This. So there is the 20 centimeter. At that time, this distance becomes also x. And at that time, this becomes our object distance. And that is our image distance. In second case, that is our first case. We have to find out the focal length of this convex lens. Right? So we can add the answer to this question like this way. Suppose at two different positions L1 and L2 of a convex lens, the image is formed on the screen. Suppose two different locations L1 and L2 of a convex lens, the image formed on the screen. Right? So first our aim is, for this case, for L1 position, what is the object distance? For location L1. So here x plus 20 plus x is given to 90 centimeter. X plus 20 plus x is equal to 90. Therefore 2x plus 20 is equal to 90. Therefore 2x is equal to 70. Therefore x is equal to 35 centimeter. Therefore object distance u is equal to minus 35 centimeter. From equation of length, so minus 1 upon u plus 1 upon v is equal to 1 upon f. Okay, after obtaining this, what is our v? There is 35, so there is the 20. So v is equal to 55. U is equal to minus 35. So centimeter. U is equal to 20 plus 35, that means the 55 centimeter. So here minus 1 upon minus 35 plus 1 upon 55 is equal to 1 upon 10. 1 upon 10. Therefore, 1 upon 35 plus 1 upon 55 is equal to 1 upon 10. Simplify it and find out what is the focal length of a convex lens in centimeter. So very easy, only here the object distance is not given directly, and also we know that as we place the object at principal focus, its image is formed at infinite distance, and if the object is at infinite distance, its image is formed at principal focus. The same thing here. So using this concept, we can calculate this numerical. Here, okay. Okay, now next is 9.21. That is depends on equation of a lens. Here, find the effective focal length of combination of two lenses in exercise 9.10. In 9.10, the two lenses are given. One is the convex lens with focal length 30 centimeter, and second is the concave lens with focal length 20 centimeter. Therefore, focal length of convex lens that is given as the F1 is 30 centimeter. For convex lens, the exercise focal length is positive, and focal length of concave lens F2 is equal to minus 20 centimeter. For concave lens, the focal length is negative. After that, the separation between two lenses, that is given D is equal to 8 centimeter. So for this combination, we have to find out the equivalent focal length of this combination. Okay. For that purpose, here, first the parallel beam of light is incident on first the convex lens. In that case, we have to find out the equivalent focal length, and if the parallel beam of the light is first incident on concave lens, we have to also find out the equivalent focal length, and we have to compare the answer of these two focal length. Both focal length are same, and notion of the equivalent focal length of system is useful at all the same point. We have to give the answer of this. Or in other words, our answer, that means the equivalent focal length, is depends on the parallel beam of light incident on any one lens. So that is depends. We have to check it. For that purpose, so here we consider if the parallel beam of light is first incident on a convex lens, if the parallel beam of light incident on convex lens, right? Therefore, for convex lens here, the F1 focal length is 30 centimeter. Object distance U1 is equal to minus infinite. We have to find out the V1. Actually, here what's happened? So there is a convex lens. Here after the 8 centimeter, here the concave lens is placed. Here the separation is 8 centimeter, and the parallel rays are incident on the lens. So in that case, what is the equivalent focal length for convex lens f1? That is the f2. So from equation of lens minus 1 upon u1 plus 1 upon v1 is equal to 1 upon f1. Therefore, 1 upon f1, 1 upon v1 is equal to 1 upon f1 plus 1 upon u1. But the u1 is infinite because the initial, whatever the light incident is parallel. Therefore, 1 upon f1, 1 upon 30 plus 1 upon minus infinite. 1 upon minus infinite. Therefore, v1 is equal to 30 centimeter. So, image of this parallel beam is focused at 30 centimeter distance this way. So, there is a v1 30 centimeter distance. This image is act as a visual object for second or the another lens. Therefore, the object distance for second lens u2 is equal to total distance 30 minus 8. So 30 minus 8 is equal to 22 centimeter distance. And focal length f2 for the second lens is minus 20 centimeter. Minus 20 centimeter. From equation of lens, minus 1 upon u2 plus 1 upon v2 is equal to 1 upon f2. Therefore, 1 upon v2 is equal to 1 upon u2 plus 1 upon f2. Therefore, 1 upon v2 is equal to u2 is 22 plus 1 upon minus 20. So it's equal to minus 20 plus 20 upon 440. So it's equal to minus 2 upon 440. Therefore, V2 is equal to minus 220 centimeter. Thus, the final image due to this combination is negative. That means on the left side of a combination is obtained. Thus, image obtained on left side of combination. At 220 minus 4, that means the 216 centimeter from midpoint of a system. Midpoint of a system. So that is the first part when the parallel beam of light is incident first on the convex lens. Now, if there is the incident on first the convex lens, the concave lens, like this way. Second part is that if parallel beam of light incident first on concave lens, like this situation. There is the concave lens, there is the convex. Separation is 8 centimeter. Here the beam of parallel light is incident. Having the focal length f2 is now here by f1, and that is our f2 for convex. Right? Okay. Now, from equation of length minus 1 upon u1 plus 1 upon v1 is equal to 1 upon f1. Here, u1 is equal to minus infinite. v1 we have to find out, and f1 is equal to minus 20 centimeter. 20 centimeter. Therefore, 1 upon v1 is equal to 1 upon f1. Therefore, v1 same as the f1 is equal to minus 20 centimeter. Now, whatever the image is formed on left side of this concave lens. Okay. This image is act as a real object for second lens. This image work as a real object for convex lens. Therefore, image object distance u2 is equal to minus 20 plus 8, that means the minus 28 centimeter. And also the f2 is equal to 30 centimeter. f2 is equal to 30 centimeter. Therefore, from equation of length minus 1 upon u2 plus 1 upon v2 is equal to 1 upon f2. Therefore, 1 upon v2 is equal to 1 upon f2 plus 1 upon v2. Substitute this value. Therefore, 1 upon v2 is equal to 1 by 30 plus 1 upon minus 20. Yes, we take the LCM of this. So there is the 13 to 28 for 20. Here the multiplication is 14 minus 15. So 1 upon v. Therefore, minus 1 upon 420. Therefore, v2 is equal to minus 420 centimeter. Here the image is formed on left side of this system, right? And therefore, the 420 minus 4, that means the 416 centimeter from. Thus, image formed on left side at 420 minus 4 is equal to 416 centimeter from midpoint of the system. Midpoint of the system. Clear this? Okay. So there is the due to the combination. Now listen. Here what's happened? Due to first we consider the parallel beam is incident on a concave. At that time, the image distance or the final image distance is large compared to the first case when the parallel beam is incident on the convex lens. Clear? Okay. Now here, the answer are not same in both cases. Thus, the answer is depends on which lens the parallel beam of light is incident. And also, the notion of the effective focal length of a system does not seems to be same at all the points. That is the difference. Clear this? So that is our first part here. Now in the second part, in this combination, we place the one object at 40 centimeter. And we have to find out the equivalent magnification in these cases. We discuss in next part. Now, in B part of this numerical, an object of 1.5 centimeter size. That means the size of an object with the height of an object is That is the h is equal to, so the h1 is equal to 1.5 centimeter. Is placed in the side of a convex lens in this combination at 40 centimeter distance from the convex lens. Therefore, object distance u1 is equal to minus 40 centimeter. So, find the equivalent magnification of this combination of system of two lenses, and also the size of an image. The equivalent magnification, or the effective magnification M we have to find out, and also size of an image. We have to find out each two. So first, for objective lens, for convex lens, object distance u1 is equal to minus 40 centimeter, f1 is 30 centimeter. We have to find out the v1. Okay, now for that purpose, the equation of lens, minus 1 upon u1 plus 1 upon v1 is equal to 1 upon f1. Therefore, 1 upon v1 is equal to 1 upon f1 plus 1 upon u1. Substitute the value. So 1 by 30 plus 1 upon minus 40. So here the LCM is 1200. So here the 124 minus 3. Therefore, 1 by 120. Therefore, V1 is equal to 120 centimeter. So V1 is equal to 120 centimeter. And now, what is the magnification? What is the magnification by a convex lens? Therefore, magnification is M1 is equal to V1 upon magnitude of U1. Here only we consider the magnitude of magnification. Therefore, 120 upon 40, that means the 3 is the magnification. Now, whatever the image formed by the convex lens is act as a virtual object for second lens, that means the concave lens. The image formed by convex lens work as a virtual object for concave lens. Therefore, object distance U2 is equal to, what is the U2? So 120 minus 8. 120 minus 8 is equal to 112 centimeter. Focal length of the concave F2 minus 20 centimeter. We have to find out the V. From equation of lens, so minus 1 upon U2 plus 1 upon V2 is equal to 1 upon F2. Therefore, 1 upon V2 is equal to 1 upon F2 plus 1 upon U2. Substitute the value 1 upon V2. Here F2 is equal to minus 1 upon 20 plus here U2 is 1 upon 112. Therefore, as is simplified, so we obtain the value of V2 is minus 24.9. Therefore, V2 is equal to minus 24.9 centimeter. So here, the image is formed on left side of this combination. right? Okay. And magnification is magnification. What is the magnification for this? So there is the M2 is equal to V2 upon magnitude of U2. V2 we obtain 24.9 upon 112, I think. Object distance is 112, therefore 0.219. 0.219. Therefore the total magnification or the effective magnification M is equal to, already we obtained for the combination of the lenses, the resultant magnification is M is equal to multiplication of the magnification due to its lenses. That means the M is equal to M1 into M2. Already M1 is 3. M2 is equal to 0.219. 0.219. Therefore 0.651 is the resultant magnification or effective magnification of the object of size 1.5 centimeter. Okay. Now we know that the M is equal to height of an image to the height of an object. Therefore H2 is equal to M into H1. M is 0.651 into H1. H1 is equal to 1.5. So find out yourself the size of an image. Size of an. Here is only the application of the Gauss law and also the equation of magnification and combination of lenses. Okay.